Good morning, myself Mukesh from Samara University, Russia. Before I start to my presentation, I want to briefly introduce myself. I complete my bachelor and master degree from India, then pre-doc from Belgium, PhD from Brazil. It was Brazil-Italy government scholarship, then postdoc from USA, and I was also a honorary fellow in UK, so get a certificate from UK. I also worked in Indian Space Research Organization as well as NASA, and as a faculty worked in India, Czech Republic, Germany, Japan, and France. Last year, I came in contact with your professor, and this is the seminar on GIS. So he suggested me to give a presentation on a GIS webinar for actual and practical applications. I worked in different countries, and that's why I briefly introduce all practical exercise or what I did the work in that countries. In my presentation, I will be explain that things. So the title of my presentation is GIS for Management and Sustainable Development. You, I think, already aware about the how satellites are moving on the Earth and provide the information and how we can use them in GIS. But before I start to my publication, I want to briefly make a background about remote sensing and GIS within few slides. Later on, I will come directly on that topic. So this is the basic slide. I think you all aware about satellite remote sensing. When we save the information in thematic layers, it's GIS, GPS working when 24 satellites come in a range. Digital image processing, we can play with the digits in raster images and make different type of thematic layers or get informations. Thermal and microwave remote sensing, getting more information with the help of microwave remote sensing, aerial photogrammetry, cartography, and GIS applications. Every field we can use remote sensing and GIS. So I will not go in more details here. And I think you are aware about remote sensing means the data acquisition about an object, area, or phenomena with some distance and without physical contact with the object. That is called remote sensing. So what is the GIS then? So when we have information from satellite data, field data, or other socioeconomic data, or anywhere else from any government department, so what we do with that type of information? So we capture this information, store somewhere, then update it, manipulate it, analyze something, manage something, and present all types of information in spatial or geographical data. That is called GIS. So when we have data, we have information, we make it in some module and provide answer of all types of queries related to that information. So that is called GIS. It's a background, so I will not be a step longer time here and want to go further slides. I think you all aware about these basic slides, how remote sensing is working, platforms and data types, and then we are users. So our GIS is come here because when we save information in different type of thematic layers, they provide answer of our queries. It's a basic slide, so I think it's not good to take too much time here. And you all are aware about the components of remote sensing and GIS, how energy pass through the atmosphere, then interact the surface and provide information to us, how information is going from one place to another place, who is the courier of the information here. These are the electromagnetic spectrum, and these are the basic things, so I think you all aware about this. Now main thing is, before I start with GIS, we need to go digital image processing, and we must know about DIP, digital image processing. What is this? You know, the spectral curve, each object on the earth provide different type of reflectancy, and this reflectancy means over a pixel. You know, the satellite image or imageries, they have in row and column format, and each pixel have some specific digits that is used in digital image processing. So before going in GIS, we make geometric correction so that each pixel open its exact location on the globe. We use change detection techniques to know the changes, image enhancement for better interpretation, band ratio or combinations to make a specific theme-oriented object like NDVI or water resampling. When we convert one data to another format, we use resampling techniques like binary, cubic, nearest neighborhood. principal component analysis. Sometimes we have large amount of information on data or thematic layers, heterogeneous data. So we use here principal component analysis and compress the information within 2 or 3 bands, and maximum 99% information stored in these particular bands. And in last, supervised or unsupervised classification. So by this way, we convert our pixel-based raster information into polygon-based vector layer and save that information. So this is the GIS here. So GIS have again 3 forms: point, line, and polygon features, and whole any type of information convert in these 3 formats and save in GIS. So that is GIS. Later on, anybody can change or update or manipulate this information. That is GIS. This is again basic slides about sensors, platforms, or active or passive type of remote sensing. The important thing in GIS is resolutions, spatial resolutions, spectral resolutions, radiometric resolution, and temporal resolutions. You, I think, aware about these things. Spatial resolutions, so the pixel size of the image, spectral resolutions, or number of bands, radiometric, say the gray levels, how bit data, like 8-bit data, 16-bit data, and temporal resolution, so the repeativity of the satellites. If resolution is high of the image, no matter it is spatial or spectral or temporal resolutions, we collect more and qualitative or accurate information. That is the base of our GIS. So if our resolution is high, then our information will be high or qualitative, and our model will be highly accurate. So resolution is important in our research work. Now we have different types of satellite data which are using in GIS, like aerial photography, multispectral satellite images, radar or microwave images, and hyperspectral sensors. In hyperspectral, we have large number of bands. They are very narrow bandwidth, and so that's why they are interact with each and every features on the ground and very sensitive. Each data have their own specific advantage and disadvantage and useful for remote sensing and GIS. I will not go in more details here because it's really basic things. So now the importance of GIS. Now we have a lot of thematic layers or different types of data. We compare them and get a thematic map or result map that will provide the all information about our queries. So basically large amount of data needed that can provide easily from remote sensing. It's reduced manual work, and it's also possible in difficult situation or impossible research sites like open ocean, hazard terrain, ocean depth, atmosphere. So allows of the collection of much more data in a shorter amount of times, because leads to increased land coverage and increased ground resolution of a GIS, and this information also can directly utilize for a visual aid or else map, or indirectly we can use for land cover, atmospheric emission, vegetation, water bodies, cloud cover, and change detections. So till today, actually I am working last 10 or 15 years in remote sensing and GIS, and I can say that in every field we can use remote sensing and GIS, like urbanization, transportation, agriculture, natural resource management, national security, and many more. So everywhere in each field we can use remote sensing and GIS. So here till I think these are the basic slides, and I think here you know or aware about what is the remote sensing and what is the GIS. So GIS is simply number of thematic layers or number of informations which can provide and the answer of our queries according to their background, or we can update it, manipulate it, or change these informations. Like when I completed some research work and save in GIS module, later on after me, any other researchers can update and change this information or manipulate it according to current date. That's why GIS is very flexible and provide more opportunities to change or to update the information. And it's really less time consuming and less price, because once our model is ready, we can easily update it. So till here I make some background for you what is the remote sensing. Now as I told you that I was working in different countries like Russia, Brazil, USA, Czech Republic, Germany, UK, Japan, France. Right now I was also planning for Hong Kong, but it was not possible due to COVID situation. So briefly I will be explaining the work that is really GIS work, using some information or data and save the information in GIS module. And I will be explaining one by one to all of you. Actually, my background was biology, zoology, and chemistry. So, and then remote sensing, then environment. So, last 2 3 years, I am focused on environmental or ecosystem or ecological work through remote sensing and GIS. So, this is my current work. So, I will be explaining about you how GIS is important and how we can use satellite data or other type of information or data and save these information in GIS and how it's useful for us. So here you can see natural resources. If natural resources is disturbed, then it's also disturbed to ecosystem health and later on its effect human life. So ultimately everything is effect on global climate change, because if you see that sometimes somewhere is industrialization or urbanization, there are a lot of land use land cover changes and they are directly degraded the climate or environmental change. And these changes speed is much faster than self-reassemble speed. So when they are degraded, they have lost the actual situation and it's a harmful condition for our climate or for our ecosystem. And sometimes it's create new problems like air pollution, noise, traffic jam, temperature and humidity variations, uncertainty and difference in rain intensity. I also noticed that sometime or maximum time governments are more focused on economic development of the country or particular city or region on the cost of ecosystem health degradation. They are more focused on economically, but not they are care about ecosystem health. So how we can get the information about our ecology or ecosystem and save in GIS module. So here I find 5 parameters like soil, water, vegetation, biology and atmosphere. These are the basic contents and they are related to ecosystem. So when we compare them, their study, we get ecological response. These are the steps you know about basic of remote sensing or DIP. So I will be not going more details here. So ultimately our target is to getting thematic layers from the satellite data. The good thing is here all these parameters can generate from the remote sensing satellites. So I generate DM, evaporation, light index, LULC, terrain, roughness, temperature and many more, around 15 thematic layers, or you can call it indicator. So one thing is they have put negative impact on ecosystem, because that's why I called them pressure indicators. They reduce the quality of ecosystem and put a negative impact and pressurize our ecosystem, so that ecosystem is going to degrade. So I called them pressure indicator. In another side we have NDVI, leaf area index, fractional vegetation cover. They reduce the pressure of these pressure indicators and try to balance the situation. So they called state indicators. So when we minus state indicator from pressure indicators, we get response indicator, and that is so the ecosystem health. That's why the complete module is called pressure state response framework. Again, here I have 15 indicators, but they are from different sources in terms of resolution, cell size, other things. So before we start to our work, we must be standardize the data, particular fixed range from 0 to 1 or any, then rescale them in same spatial or temporal resolution, so that each indicator gets similar weightage or importance in our results. Otherwise, one parameter affect our results. So these are the basic things. So here we complete that type of module, put these input layers, around 15 thematic layers, and get results and save in GIS format. And that is give the answer that how is the ecosystem health here on the globe in particular study area. I did this research work in Samara, so it's the ecosystem health in Samara in GIS. Now, how can convert this thematic information in ecosystem health? For that, I use this equation and give specific weightage to each thematic layers and generate ecosystem health. Here we have some relationship between pressure, state and response indicator. When we minus state indicator from pressure indicators, we get response indicator. If pressure indicator is high, then high ecological disturbance is present. There are instability and there are a lot of changes in environment, and that is the worst situation. Means pressure must be reduced. In another way, if state indicator is high means everything is stable, there is less environmental changes, and it's a stabilized ecosystem, and it's good for sustainable development. And in last, we can say that low response indicator represent a stabilized ecosystem, and it's good for sustainable development. I think here you understand what is the pressure indicator, what is the response or state indicators, how we can get ecosystem health. So once we get the ecosystem health, we can manage, update our study area, government make the plans. If the ecosystem health is very high and degraded condition, then government will be make another type of plans for that area. As I told you that I use 15 thematic layers. So these are few layers here. DM means if we show the elevation or height information. So if we go in high elevation areas, the human socioeconomic activities are very less there, and it's safe ecosystem health condition here, but in low level it's high. Light index also effect means if light index is high means there are too much socioeconomic activities are present. So we can manage these things, and we can identify where is the ecosystem health is really good or where is the bad situation based on socioeconomic activities or the disturbance in natural resources. So basically I use these thematic layers. Here are some results in Samara. Actually, I study of ecosystem health in Samara in Russia. So here you can see that pressure indicator was slightly reduced from 2010 to 2020, and it's centralized to the city. Response indicator, so effect also reduced. This is the state indicators, and this is the resulted map. And you can see the forest area or natural vegetation area have excellent ecosystem health, but city center and other industrialized or high socio-economic activity site have low ecosystem health conditions or worst situation. So now you can ask me that how GIS is important here, because we collect the data from only satellite, make them different type of information. The satellite data is single, like Landsat, 30-meter resolution, source until, or iconographic keyboard, any data. Second thing, we convert this data and specific thematic layers. It's NDVI, Landsat, land use, or water, and any types of. Then input this information in a specific module here, pressure state response module, and then collect information or get output of the information, and that information save in a specific module that is called GIS. These are some resulted things that mean value was increased from 2010 to 15, then again reduced. So ecosystem health was earlier not in good condition, but ecosystem health condition was increased, and later on it's reduced, but not in earlier situation. Peak values was reduced, so means high disturbed area and it goes in low disturbed areas. Minimum values also increase, that is not good because it's convert low ecosystem health condition into higher vulnerability conditions. And so here is also net changes, how much area is degraded, upgraded or unchanged. So I get these information from only 15 satellite, 15 thematic layers, and this information was collected only from satellites. I was also thinking why I cannot enlarge my module, and in place of not only satellite data, must we use some other type of secondary data which I collect from satellite data, some government offices like gross primary productions, population density, fertilizers, human activity index, investment, cattle, crop, grain production, milk production, soil production, so a lot of. So the earlier study in pressure state response framework, I use only 15 parameters. Now I use 23 parameters so that my results will be more accurate, or I can say that in other words, my GIS module will be more qualitative, accurate, and provide more answer of the queries, means how much population density effect in the module or gross primary production is effective. So that's why I enlarge my module here so that my GIS will be really more meaningful. So here earlier I used only soil, water, vegetation, alleles, but now I use economic or demographic data, means human socio-economic information, which was already in vector format, so convert in raster format, and you are aware about these basic things in pre-processing. So ultimately I get these 23 parameters, and I divide in these parameters in five big parameters like the driver indicator, pressure indicator, state indicator, impact indicator, and response indicator. I already mentioned about pressure, state, and response indicator. Driver indicator means some parameters which they are initiate the pressure, and impact indicator means they get first order effect after that type of pressure. So now it's a and DPSR framework, and I give the weightage according to analytical hierarchy process and generate ecological vulnerability index. In this way, I find out where is the high vulnerability ecological or where is the low vulnerability, and that information can be useful for sustainable development if we classify the things. And these are the results, and this study was in Tatarstan, Kazan, Russia, and here you can the situation. This is the study area, and Russia is the Tatarstan state, and this is the my study area. Around 8 or 9 districts was available, including Kazan city here. Kazan is the third best tourist place in Russia after Moscow and St. Petersburg. So here you can see the highly human socio-economic activity site or urbanization area have, or the industrial area have high ecological vulnerability index, and the forest area, water body, they have low ecological vulnerability index area. And these are the changes from 2010 to 15, 15 to 20, or from 10 to 20, which class is converted to in which type of class, like here 2010 to 14. Unchanged area was very less, especially moderate and heavy class, and improved area means the classes low environmental vulnerability index convert in high environmental vulnerability classes, and degraded means high classes shift in and low classes. So these are the statistic results which get from the satellite data as well as secondary data, make them in a module and convert them in a meaningful informations. And these are the useful for government to make their policies to which area they want to really develop and to improve the situation, in particular that type of area, and how much money they can put in that system so that ecosystem is the safe. So here you can understand how GIS is important for us. So one time we have just information or collect that data. Second, we utilize this information for something theme-oriented projects and provide some good information for better management, sustainable development, and planning of natural resources, so that our natural resources must be utilized by the next or future generation. Here one more step here. So I think till here you understand how remote sensing and GIS working. I have some thematic layers earlier from satellite data only 15. Then I increased 23 with the help of secondary data like economic or demographic or socioeconomic data. Now one more thing here, I use habitat vulnerability and ecological loss. The habitat vulnerability, it's so more socioeconomic activities or human intensity, and then loss of ecology. So I make a layer or object oriented layer like LER means uh, ecological risk, or here ES means ecosystem services. So earlier land ecological risk and ecosystem services, when we correlate them or overlap them, we get some different type of information. Now you can see earlier we have just direct information. Now we make some specific combination and make three different layers: habitat vulnerability, ecological loss, and ecosystem services. Our target is always risk will be less and ecosystem services will be high. That is the ideal and good situation. Everywhere, all governments wants that their region is low ecological risk, land ecological risk, and particular that ecosystem provide high services. But sometimes it's not possible. So that's why that data is same, but we change the type of information here. We just use three different layers, make them two like LER and ES, ecosystem services and ecological risk, land ecological risk, and overlap them to exactly identify that particular these patches or area have high risk or with low ecosystem services. Some area have low risk and provide high ecosystem services, which is really good things. So by these types of work and also make some statistical test here to identify how much we are accurate, how much our data is really good, and by this way government or policymakers know the actual situation where they have high risk, where they have low risk, where they have high system ecosystem services, where they have low ecosystem services, and make the good and balanced situation and can develop easily and manage their natural resources. So the result, when we overlap LER with ES, we can make proper utilization of land and management to improve ecosystem services with less ecological risk and sustainable development. I think here you understand the data information is same, but the ultimately output or results are going different directions. So here are some changes from risk and ecosystem services in 2010, then 15 and 20, how much area is degraded in particular area, which are the unchanged and which are improved in the condition. So ultimately I can say that greenness, wetness, they put a positive effect on ecology, but dryness and heat put negative impact, and vice versa. But in Russian climate, its maximum time is snow cover, so little bit heat is really good here in comparison of Southeast Asia. High socioeconomic activities always put negative impact. Changes in mean value of indicators reflect ecosystem health patterns. Any positive response from natural resources such as crop growth, health, and dense forest and less urban area was the main pathway to improve the ecosystem health. Overall, each ecosystem health assessment is critical to regional environmental protection and sustainable development. So I can say that as a new research topic, combined traditional ecological principle with remote sensing, GIS technology, landscape ecology and ecosystem services evolution, it would have great sustainable development. So this is one work about ecology, ecosystem information, same ultimately in GIS format. Now second study I did on monitoring crop phenology, which NDY time series from sensitive to data at 10-meter resolutions. So again, using satellite data, sometimes secondary data, making analysis work and using some module and save this information in a GIS module so that which later on it will be useful and to provide some meaningful information. And it's important for like agriculture studies, useful for yield estimation, agriculture field management for food security, sustainable development of agriculture, to improve productivity. It's also important to understand how climate and local factors are effect on crop growth. So other than this, we can say that it's important for supporting crop modeling, extension, irrigation, fertilizer management, harvest determination, and in last, enhance food security. This is the Samara region NDY map for whole year from January to December. You can see NDY value is almost zero, close to zero, because area is completely snow covered in April. It's start to melt and NDY start to increasing due to seeding, and it's the peak value in July. So maximum greenness was present here, and again September, October it's start to reduce, and it's same to same like crop calendar you can see here in this graph. So satellite data provide real or actual information what is on the ground, and we can use data with field data or other combined with other secondary data and save in a GIS module and provide us a lot of meaningful information, and that is really good for us. If we compare these graphs with total area or types of NDY values, again in after April, maximum type of NDY values was present here. So satellite data or GIS provide us some meaningful information here. You can see that everyone changes in the study area in our labs, no need to go in field, so how GIS is useful here. So I just explain you two research objects here or research work here about crop and ecology ecosystem related work. Now I just briefly introduce about Brazilian work which is related to land use land evolution, natural vulnerability, environmental vulnerability, coastal vulnerability, and coastal risk assessment, or basically inundation risk assessment. This was my study area in Northeast Brazil in natal city. Vulnerability. I think you are aware about vulnerability. It's a three component: exposure, sensitivity, and adaptive capacity. Means when a entity is under state, that is called exposure situation. If it's first order effect, then it's sensitivity condition, and in last it's a coping and resilience adaptive capacity. You can understand this thing by like we have a big water pond in our study area, and it's a 10 meter water capacity. So if water level increase like 6 and 8 meter, that is exposure situation. Sensitivity means if water level reach 9 or close to 10, means after that pond will be broken and area will be flooded. So that is called a sensitive situation. And here we have two types of options: coping capacity and resilience capacity. In that situation, we try to reduce the water level of the pond so that it will be not broken and area will be safe. Or other side, increase the water capacity of the pond by building some roads or walls. Anyway, if you are unable to save our system and in that water level reach 10 meter and it's broken, so whole area is flooded. So this is the resilience adaptive capacity here. Because we are a human being, we never leave our system in broken conditions. Always try to rebuild our systems, no matter after earthquake or tsunami or any type of natural or man-made disasters, after wars. We always try to rebuild our system, that is called resilience capacity. So we can say that vulnerability is the degree to which a system is susceptible to or unable to cope with adverse effect. This is my environmental vulnerability map, and you can see that water body or forest area or natural resources like agriculture, they have low vulnerability, but industrializations, urbanizations, they have high vulnerability. I hope you understand. So now you can ask me how GIS, or where is the GIS in that. So simply you can see that I use simply satellite data or secondary data, make a vulnerability related concept or module and save these modules and produce that type of results, environmental or natural vulnerability according to their algorithm or types of information. And this is produce information like where we are highly sensitive situation or where is the low sensitive situation. I remember one time I met in Indonesia Australian professor, and he asked me that because if you know how much risk area in particular region, then why you are not economically think that how much money we put or we put in the system so that risk will be zero. And I was surprised what to say, but again we are scientists here, we can generate information, we save information in GIS module, but ultimately to implement this information, it's the second side of the coin, and it's the government. They will implement these things according to their own plans, or they can put the money in the system. So we have one side scientific community to generate the information, save the information in a GIS module, but another side it's government side, how they can utilize these information to save the people, to secure the people, and how to use this information for civilians better life. In USA, I was working on satellite generated brightness, temperature, and make some polarization and gradient ratio. It's very much similar like NDVI and generate. I was using MSRE data there, and in polarization ratio, when temperature is increase on globe, it show the desert area, and when temperature is going to reduce, it show the dense or healthy vegetation. And in GR combination also very much similar like that. MSR have around 5 frequency, and that time I make 17 land use land core classes and identify the actual physical land surface temperature. You can see if the frequency is low, they are not so actual physical land surface temperature, because water is very cold here and land is warmer. That is not possible. But if you go in high frequency, you can see the greenness have high temperature and ice have low temperature. Belt again is high temperature and built up area. So the result was, I will not go in more details here, otherwise it will take too much time. I just simply introduce you that MSR have six frequency, and both are horizontal and vertical frequency. And when we identify specific temperature for each land curve classes, it's a specific temperature, but they are not correct. But if we go in high frequency, it's the actual physical land surface temperature. This was the 89.0 vertical frequency. Same thing as I told you, PR and GR combinations, it's very much similar like NDVI. So ice, snow, or water have very far in the graph, but vegetation is close to zero. So I will not go in more details because it will take too much time, but here you can simply understand that GR have very much like NDVI values from -1 to +1, but polarization ratio start from 0, and in particular one range more than 2 or 3 classes are present. So that time I was working, is this satellite data is really useful for land use land core classification, and the result was this table that this is a good quality data, but only for first level land use land core classification is good, but for second level or third level we need to improve the quality of that data. So here the GIS help us that okay, we have satellite data, but how much it's qualitative to generate the information, or to what level of information. Again, these are the snowcore map on northern hemisphere. That time I was Nova. This is January situation, April situation. Later on it's July, and then October. So snow was like, if here 100%, this is 75. It's only around 10 or 20%. This again increased. I think this is only 3%. This is around 20 or 25% snow cover. So whole year snow cover situation. So simply satellite data, but its type of snow as well as how much area is covered, that is the GIS. So maximum snow was below than 5,000 meter elevation, and during April it goes upside. In July it's above 5,000 meter elevation, and then again October it's come to downside. So I complete Russian, USA, and Brazilian study. Now it's the simple land use land core map study in Czech Republic. These are the cross tables of land use land core, where which class is increasing, how much differences was there, making some cross tables to which class convert in which type of class. So this is the GIS. Again, this graph showing in particular 3 locations, that if we come close to city center, urbanization area is increasing and natural resources are reducing. But when we go far from the city center, natural resources increasing. So these are the information we can get. These are some field photographs of my when I was in Czech Republic during the field work. This is a UK map. That time I met with the professor Ballard, and we discussed, is it possible to collect the actual physical land surface temperature, particular different satellite data, Landsat, MSR, and Astra data, and which data provide actual and real highly qualitative. And I get some results from that, and it was really nice study to identify temperature information on the globe from anywhere on any location on the globe. Now it's Germany River University. I was working on Kuala Lumpur, Manila, and Singapore cities and their development from 0 to 50 kilometers from city center, and what type of classes increase. So this red color is for the built up area. So you can see where city is growing in which direction. Here you can see in 89, then green phase, so 2001, and blue color is 2014. So where city in which direction is moving from city center, and how much area is covered. So how with the GIS help we can easily identify these informations, which is really meaningful. And if I go more in depth, you can see here this is the density map of Kuala Lumpur city from city center. Here you can see from city center, the maximum density was above 90 meter, 90%, sorry, and in 2014 it's little bit increased. But if you go like here from 6, 7 or 8 or 9 kilometer from the city center, in first half from 1989 to 2001 city density was increased here very high, but later on it's not increased like earlier time from 2001 to 2014. So by this way, it's a simple satellite data in a GIS module. We easily identify where or what type of information, like here city density information. We can easily identify particular locations from city center to 50-kilometer distance, and government can use these resources for their proper planning or management. In Japan, I was working again, notice, so it was land use, landfall maps. I used this thematic layer: vegetation, wetland, geomorphology, geology, soil, and their subclasses, give specific weightage and generate environmental boundary map. And you can see the results here and natural boundary map. I also work on DM there, and here you can see if water level increase only 1 meter, then 10% study area is covered by the water, and on 10 meter 29 or 30, almost 30% study area will be flooded. So this is the situation from 1 meter, 2 meter, 3 meter, 5 or 10 meter, means particular what class or what area will be flooded every meter increase of water, and maximum affected class was the wetland. So GIS is help us where we are, what we want, and how we can read the information. Data is the same, information is the same, but once we save this information in GIS module, it will provide the answer according to that one. In Bonn University, Germany, that time I was working on Aravalli Basin area, Myanmar, for food vulnerability and food security, because population is continuously increased and the demand of food is continuously increased, and maximum area was there, like food insecure area due to flood plain. So I use around 11 parameters, and with the help of PCA I make the relationship between the all parameters. Means if population increase, demand of food is increased. If we are using fertilizers, production will be increased. So some have very high correlation, positive and negative, and making some thematic layers like erosion danger level, land degradation maps, harvest failure, and generate food vulnerability map. Here you can see that around 50% area have enough food, and only 4% area have insecure or insufficient food in the Myanmar in Aravalli Basin region. So ultimately, they using alluvial farming, means the area is flooded during rainy season, and later on when what is away from that is provide a good land and fertile land which have sufficient irrigation of water to provide agriculture, and people using for agriculture purposes there to compete the market demand of food. Now here you can ask me that we are talking data. Ultimately, we can divide our data in two parts. One is remote sensing data, and another is conventional data or field data or secondary data or different government organizations data. So I can say that conventional data are more accurate, site-specific data collection is time-consuming, expensive, require more manpower, and it may not be possible to extrapolate to a large area. But remote sensing data, on the other hand, have got advantage due to repeated and synoptic coverage of the large inaccessible area and quickly and economically. That's why to take the dual advantage, it's good to use both type of satellite data. Here I use these equations for urban growth studies here. So you can see this is the Samara city. This is the biggest European river called Volga, and this is the city center. In 75, 85, 95, how city is growing continuously. One interesting thing here, you can see the built-up area was in slightly increased from 75 to 95, but dramatically reduced from 95 to 2005, and then again start to increase. I really surprised that how is it possible? As cities increased and then immediately reduced. So to verify this, later on I will tell you. So these maps again show you which area convert, how much changes, where they are unchanged, and which class convert in which type of class through the cross tables. Like here, this is the forest map, grassland, water, and built-up area. So as I told you that city was increasing, so this is the built-up map, and till 95 it was increased and reduced. So I compared this information with population map, and I found that until 1991 the population was increased and then dramatically reduced. I think this was the situation in USSR break, and after 2010 again population increased, and same thing was present in our satellite image, that built up area was increased and later on it's reduced and then in last again start to increase. We can also find any type of information like annual change rate, expansion rate. So our GIS is really a very powerful tool which can provide the all type of informations. In which year, what type of or what city part was increased, you can easily identify in these maps. Now another type of study is groundwater potential zone. In that I use some parameters, gave them specific weightage from 1 to 9 as according to this table, and identify where is the more or low groundwater potential zone, and each indicators pairwise, make some pairwise and give importance from 1 to 9 and get weightage from like normal weightage or geometric mean, like that from these types of equations, and the resulted map is so this type. So this is the resulted map, and you can see that uh, around 35% study area belongs to moderate type of groundwater zone. These are the really, again you can ask me that sometime we using the same, it's the same satellite data, and sometime using for groundwater, sometime agriculture, sometime food vulnerability, sometime ecosystem. So no matter what data we have, ultimately our GIS is a powerful tool to convert these information in what type we want. This is again hyperspectral data. As you know, multispectral data, pan data, and hyperspectral or macro data, or each data their own specific quality. As hyperspectral data have large number of bands with narrow bandwidth, so each bandwidth due to narrow bandwidth, it's more penetrate or more easily interact with the specific theme-oriented objects, even till mineral level study in geology. So I was thinking, is it possible to classify all features with the hyperspectral data in compare of multispectral data? So here I compared hyperspectral data with ALI and OLI data, and I get this type of result. In that, in hyperspectral data, each class easily separate, but in multispectral data it was not possible. Even in the maps you can see. So when we have large number of narrow bandwidth, we can easily classify maximum or till third level land core classifications, or separate out the features in compare of low bands or only few number of bands. This is European Russia, and there I was study on vegetation drought dynamics, how rainfall and temperature or vegetation interact with each other and make them meaningful. So in European Russia, I make 25 rainfall stations and collect rain informations, and this information was in SPI, standardized precipitation index. When values are so SPI, if it's a +2 means it's extreme wet, and it's -2 means extreme drought. Here you can see that from 2000 to 2004 it's a negative value, then again positive means wetness and dryness, and these are the changing points. Again 2010, then 2017, and at the same time I also make a DI map with vegetation and no vegetation, and vegetation again dense, open or degraded vegetation. So the rainfall map is also according to SPI index. Here you can see the values and identify where is the wet region, where is the dry region, or drought index. So all graphs are similar to go according to SPI index here. time is going very fast, so I don't want to stay a long time here, and little will go faster here. So ultimately you can see these results. The vegetation is increased, then reduced, then again increased. It's the same like what we say in this map here. So our results can indicate that the analysis of three primary data, rainfall, land surface temperature, or vegetation indexes, has some relationship between climate condition and its direct effect on vegetation through the reduce in rainfall, high land surface temperature, which is increase the drought occurrence, and indirectly from human interference. So one side is human interference, then its effect on rainfall, then it's again effect on temperature, and then effect drought occurrence. So each things in ecosystem, they are correlate to each other. Last time I was also met with a Chinese professor, and in that time we make landcore map of the Southeast Asia. So these are the maps and various from 2010 and 2009 to identify the changes. Thanks for your patience, and I try my best to complete all things within 45 minutes. And you are most welcome to ask me anything related to remote sensing, GIS, geoinformatics, how we collect the data, what type of data we can collect, how we can utilize. Right now, magazine tools are using big data, machine learning, lot of programming, because we have data, and how we can utilize this data, what type of informations we can do that type of things. So technology is day by day is increasing, and it's really we need to make this technology meaningful theme oriented objects or projects or meaningful informations to solve our problems or make a better life of civilians. Thanks for your patience and you are most welcome to ask me anything. Thank you. Have a great time.